Hi, everybody. Welcome back to Statistical Methods. This is Week 3, Lecture 2, where we will be talking about the normal distribution, sampling, and probability. So let's get right on into it. So as a recap, the goal of Week 3 is to begin easing you into several concepts that will become crucial later on in the course. Specifically, number 1, the ability to quantify the extremity of a statistic within a distribution comprised of that statistic. So we talked about that in the last lecture in regard to z-scores. And number 2, knowing things about how the distribution of a statistic looks so that we can make probabilistic statements about scoring at various places along the x-axis. So for example, what is the probability of finding a z-score greater than 1 or lower than -2? So last lecture, we covered how to quantify the extremity or distance of a score from the sample mean of a single score within a distribution using a z-score. So again, z-scores tell us how many standard deviations away from the mean is this particular score. Now today we will cover learning how to make probabilistic statements about scoring at or below or at or above a statistic, assuming that a statistic is distributed in a certain way. So when all scores in a distribution are converted to z-scores, this is called a standardized distribution of z-scores, and it will always have a mean of 0 because the sum of x minus m deviation scores always works out to be 0, and a standard deviation of 1 because everything is divided by the sample standard deviation. So z-scores always have a standard deviation of 1. However, the overall shape of the distribution will match that of the original raw score distribution. So, for example, if we're dealing with a raw score distribution with a left skew or a negative skew, like the one on the left here, of a distribution that has a mean of 5.93 and a standard deviation of 2.25 when we're looking at that distribution of raw scores. Now, the z-score distribution, when all of those scores in that distribution here are converted to z-scores, will still have the same shape. There will still be a left skew. However, the mean of this z-score distribution will be 0, and the standard deviation will be 1. The same is true for symmetrical distributions. So if our raw score distribution here on the left has a symmetrical distribution, when we convert all of those scores to z-scores, the z-score distribution on the right will also have a symmetrical distribution, but the mean will be different, of course, a mean of 0 and a standard deviation of 1. That will always be the case for standard distributions of z-scores. Now, if the distribution of raw scores has a right skew or a positive skew, the z-score distribution, when all of these scores are converted to z-scores, will also be skewed to the right, or a positive skew. Right, again, so that means the tail is on the positive side, or the higher side of the distribution. And the mean of the distribution will be 0, and the standard deviation will be 1. So when we know that the distribution of a statistic matches a probability distribution with known properties, like the bell-shaped normal distribution we'll talk about today, we can begin to make probabilistic statements about scoring at various values along the scale. So first, let's break down what exactly a probability distribution is, and then we'll talk about the normal distribution in particular, which serves as an example of one of these. Now, probability distributions are mathematical functions that provide the probabilities of occurrence of different possible values of a statistic. So as most statistics we'll learn about in this course are continuous rather than discrete variables, we'll typically talk about probability density functions, or PDFs. An important thing to understand is that a probability density function is used to specify the probability of a random variable falling within a particular range of values, as opposed to taking on any particular value. Because the variable is continuous, creating an infinite number of possible values, the probability of scoring any one specific value is 0, since there are an infinite number of values. And the probability distributions we'll deal with in this class will look something like this. Now, the probability of scoring between two given values on that x-axis, or above a particular value or below a particular value, etc., is equivalent to the area under the curve between those points on the x-axis. So you could find your probability by calculating this area here of scoring less than 15 on this particular variable. So the probability of scoring at or below 15 is represented by the area under the curve. Now, the way to get the area under the curve is by taking the integral of the probability density function over the specified range along the x-axis. Luckily, though, we have software and online tools we rely on in this course to give us these probabilities directly, given particular values of x, or values along the x-axis. So we'll never actually have to do this calculus ourselves. The first probability distribution we'll learn about in this class is the normal distribution, and it is a symmetrical, bell-shaped distribution. So when I say that this is a distribution whose properties are known, what I mean is that once we know that a statistic is normally distributed, so that means it is distributed like this in our particular sample, we can answer questions about how probable various values of that statistic would be. So for example, what is the probability of scoring between z equals 0 and z equals 1? Or between z equals -1 and z equals 1? Or of obtaining a z value greater than 3, or a z value lower than -2? So another way to think of these probabilities is in terms of percentages. So 68% of participants in a normally distributed variable will score within one standard deviation, either negative or positive, of the mean. So a probability of 0.34, or of scoring between z equals 0 and z equals +1, is equivalent to 30% of scores are expected to be between z equals 0 and z equals 1. Now, IQ tests are standardized to have a mean of 100 and a standard deviation of 15. And because IQ scores end up being roughly normally distributed, we can estimate that around 68% of people will fall within positive or -1 standard deviation of the mean. And that is represented by an IQ of either, or rather between 85 and 115. We could also ascertain that around 96% of people will fall within positive or -2 standard deviations of the mean. So that's from here to here. And we also know that almost everybody falls within 3 standard deviations of the mean. So from here to here. Now, IQs above this level are referred to as genius IQs. And only 0.1% of the sample, or the population, have such a high IQ. Now, these percentages are the same for any normally distributed statistic. So converting all of the scores in a distribution into z-scores won't guarantee that the distribution of z-scores ends up normally distributed. So that means that we can't start making these kinds of percentage estimates for a variable unless it is normally distributed. But as mentioned earlier, this example, which is converting all scores in a sample to z-scores, isn't frequently done in the real world. Rather, most of the statistics we'll learn about will be calculated based on the entire sample of participants, that is, based on a sample mean, as opposed to an individual score. And for reasons we'll learn later, these statistics do end up following specific known probability distributions like the normal distribution. So we will be able to make probabilistic statements about obtaining values on scales, even when those scales aren't normally distributed in our sample. So when our variable's distribution is normal and we convert all of our scores to z-scores, we end up with what is called the standard normal distribution, which is a normal distribution with a mean of 0 and a standard deviation of 1. Thus, the standard normal distribution is just a special version of the normal distribution, where all scores are standardized with z-scores. Now, the standard normal distribution has columns displaying the positive z-score, the percent of scores expected to fall between the mean and that z-score, and the percentage of scores expected to fall between that z-score and its respective tail, whether that being the positive or negative tail of the distribution. Now, the page number here might not be correct for this, but you can find the normal distribution table in the back of your textbook. And we won't really be relying on this table so much. We'll just use it in this lecture as a demonstration. We'll be using a Shiny app, which I'll demo towards the end of the lecture, to find probabilities associated with particular z-scores in the standard normal distribution. But here's an example of a z-score in that z-table or that standard normal table. So a z-score of 0.52, meaning roughly half a standard deviation above the mean. And the probability in the tail is displayed as 30.15%. So that means that 30.15% of scores in a distribution, in a standard normal distribution, will be above a z-score of 0.52, will be higher than a z-score of 0.52. Now, if we wanted to express this percentage as a probability, that would be 0.30. So I want you guys to practice using this standard normal table with another data set. So a sample of self-described atheist, spiritual, and religious participants were recruited for a study on differences in language usage when describing their beliefs or lack thereof. And in this study, all participants completed a 1 through 7 scale of belief strength. And mean scores were calculated for this scale. And these scores were found to be roughly normally distributed with the following characteristics. Subjects scored an average of 4.05 on the scale, and the standard deviation was 1.40. So using the standard normal table, what percentage of people would be expected to score at a 6 or above on this scale? So the two pieces of info that we need to do this is what is a 6 in z-score terms, and what percentage in the tail is associated with that particular z-score. So first we calculate the z-score. So our score is 6 minus the mean of 4.5 divided by the standard deviation of 1.4 equals a z-score of 1.39. So that means a score of 6 is 1.39 standard deviations above the mean on this variable. Now if we go to the z-table or the standard normal table, we could ask the question of how many people score above a z-score of 1.39 or a raw score of 6 if we convert that back to the raw score. And we look at the table, line it up with that particular z-score, and look for the probability in the tail, which will be the upper tail, demonstrated right here. So we go to the table, z-score of 1.39 is associated with an 8.23% chance of winding up with a score as extreme or more than a 6 on the scale. So that means a 6 or higher. Now, if we wanted to figure out how many people score below the z-score of 1.39, we can look in this column here, the percent mean to z. So that's the percentage of participants scoring between the mean and that particular z-score. And the percent mean to z associated with 1.39 is 41.77. But we also need the other half of the distribution as well. So that's the half on this side of the mean. If you see where my cursor is pointing. And because we're dealing with the standard normal distribution, 50% of scores should be on either side of the mean. So if we add our obtained 41.77% to 50 for the other half of the distribution, we find that 91.7% or 77% of scores are below this z-score of 1.39, or a 6 on the raw scale. So note that these numbers, percentage above and percentage below a score, should always add up to 100. So what about negative z-scores? The table only gives positive values. What if somebody scores a 2.5 on the scale? So that's the raw score. So to find the z-score, you'd take that score, 2.5 minus the mean of 4.05, divide it by 1.4, and we got a negative 1.11. So step one would be to find the positive form of this value on the table. So z equals 1.11 in the positive direction. And we find that 36.565% of scores fall between the mean and this value, and 13.35% of scores are above this value. Now, if you just think about the symmetry of the normal curve, you can get your answer. So if the percent between the mean and this value is 36.65, that means that 36.65 plus 50 equals 86.65 of people score above z equals negative 1.11, whereas 13.5% of people score below this value. So basically all you need to do is, if you're looking for that tail probability, change the word above to below to find your probability for a negative z-score using this table. So here are a few tips for using the standard normal z-table. So always begin by visualizing or sketching where your z-score would fall in the normal distribution. And then compare the numbers you find to what makes sense based on this visualization. Should the percentage above or the percentage below be a large or small number? Now for negative numbers, negative z-scores, imagine that the mirror images of the shaded regions displayed in the table. So going back to that table, now here's the positive representation of the tail probability. So imagine the mirror image of this if you're dealing with a negative number. You're dealing with something over here. So for example, the percentage in the tail now communicates the percentage below this score, not the percentage above the score, when we're dealing with a negative z-score, which is simply a score converted to a z-score that falls below the mean. So now I'm going to show you a cool tool for visualizing the normal curve and adjusting z-scores to find the probability of somebody scoring as or more extreme than a given z-score. So that is the tail probability of obtaining a particular z-score or more extreme. And you could also adjust the probability and do this in reverse to find out what z-score someone would have to be in the top or bottom 5% per se. So if you click on this link, you'd be able to follow along with me. Now this is the tool I will want you to use to obtain probabilities for z-scores on quizzes, because it expresses z-scores and their probabilities in terms of probability rather than percentage. And you don't have to deal with not having anything to look up negative z-scores without having to do some extra steps. So there aren't any extra steps for finding probabilities of particular z-scores in this particular tool. So click on this link. So this is the Shiny app for the standard normal distribution, or the z distribution. And what I want you to do, if we're going to look up the probability of obtaining a z-score as or more extreme than a given value, is go to this option box here and select value 2, which is adjust x-axis quantile, or the z-value. And we'll start out talking about positive scores. So we're going to select one-tailed upper probability. And instead of a slider, I want you to use a number entry box so you can specifically enter the particular z-score you want to look up the percentage for. So let's say a z-score of 1 to start out. So here is our z-score of 1. And again, that means 1 standard deviation above the mean. So if a score is 1 standard deviation above the mean, you'll see our probability expressed right here as a decimal. So this is 0.158. And what this means is that the probability of obtaining a score 1 standard deviation or higher above the mean is equivalent to 0.15866, or expressed as a percentage, 15.8%. So 15.8% of scores are at or above 1 standard deviation above the mean. Now, a z-score of positive 1.65 is roughly 0.049 probable. So that means only roughly 5% of scores are above 1.65 standard deviations above the mean. Now, if I wanted to look at a negative z-score, you would use the one-tailed lower. So that would mean, let's say we have a z-score of negative 1.65. The probability of obtaining a z-score as deviant from the mean or more, so that is obtaining a z-score of negative 1.65 or lower, is again roughly 5%. So 5% of scores in a standard normal distribution are lower than 1.65 standard deviations below the mean. So you could use this if, let's say on a quiz, I were to give you a particular z-score, and I were to ask you, what is the probability of obtaining a z-score this extreme or more from the mean? You would look up the probability in this Shiny app by selecting this here. You're adjusting the axis quantile, so the z-value. Now, if that score is negative, the z-score that I provide to you, you'll use the one-tailed lower. But if it was positive, you would choose one-tailed upper, select number entry box, and enter the z-score I gave you. Let's say I give you a z-score of 2. And I say, how probable is it that somebody scores at or above a z-score of 2 in a standard normal distribution? And the answer you would give to me on the test would be 0.02, rounding to that nearest hundredths place. Expressed as a percentage, this would be roughly 2% of people score at or above 2 standard deviations above the mean. So I'm going to close out the lecture by talking about sampling, populations, and probability to tie this all together. So imagine a linguistics professor has helped develop a new language learning app and wants to test it out. So what this professor wants to know is how effective is this app in comparison to other popular language apps like Duolingo for people in general. So an impractical way to go about this would be to try to get enough investors and grant funding to test the efficacy of this program on every adult alive in the world. So that would be the entire population of interest. But a better way to do this would be to test out the software on a smaller group of people, so a sample that matches the characteristics of the general population enough for us to assume that any statistics calculated based on that sample would approximate the true value of those statistics for the entire population. So the logic here is that we are collecting a randomized representative sample from the population of interest. We're manipulating the independent variable and measuring a dependent variable or variables, and then using these data to make inferences to generalize to the population of interest. So this is the logic behind inferential statistics. Now, the purpose of social science research is really to be able to say something only about the actual participants studied. Generally, we want to make generalizations about the greater population of interest. Now, the ideal method for sampling is random sampling. So, beginning with a complete list of the entire population of interest and randomly choosing from this list to create your sample. Now, this gives us the best shot at collecting a sample that is representative of the population at large. Now, truly random sampling is typically not possible or practical, though. Most people rely on some form of convenience sampling or recruiting participants based on who is available, willing, and or required. For example, class credit to participate in a particular research study. So why does the sampling method matter? So to be able to generalize to a larger population, we need to make sure that there are no important differences between the sample that we choose and the population we're interested in. So for example, if a professor who teaches an 8 a.m. class asks all of his students, how much of a morning person are you? And then tries to generalize his findings to the entire population of undergrads, there are going to be issues because this sample that he chose is likely going to have morning people in it since the class is so early on in the day. Only people who are morning people would really sign up for this course. So really, from the sample, we can't generalize what we find in that sample to the population of interest, which is all undergrads in this particular case. So the goal in all of this is to estimate the values of population parameters, which is the term used for statistics like the mean, variance, and standard deviation that describe entire populations of individuals. These are contrasted with sample statistics, or numbers based only on the actual observed data collected from a sample of the larger population. In most situations, we can't know the true population parameters, so we use samples to approximate them. So the larger and more representative your sample is, the closer the calculated sample statistic will be to the true population parameter. So in notation, statistics use different symbols to refer to statistics and parameters. So sample statistics are denoted by Roman letters like M, SD, and R, whereas population parameters are denoted by Greek letters like mu and sigma and rho. So for example, at the sample level, so statistics, means are represented by M, as you've seen, standard deviations as SD, and variance as SD squared. But at the population level, these parameters are known as mu for mean, sigma for standard deviation, and sigma squared for variance. So notice here, these are Roman letters, and these are Greek letters. This is how statisticians differentiate between population parameters and sample statistics. Now, probability, or P, is the relative frequency of a particular outcome, ranging from 0, impossible to occur, to 1, certain to occur. This is why you've seen probability expressed as a decimal in Z-tables and the Shiny app. Probability is an essential ingredient in understanding inferential statistics, and all of the inferential statistics that we'll learn to carry out will rely upon this type of probabilistic thinking. So probability equals the possible successful outcomes divided by all possible outcomes. So that's a little bit hard to understand, but if we look at some examples, it will become clearer. So the probability of me flipping a coin and getting heads would equal 1, the number of ways to get heads, right? There's only one way to get heads. It would be the coin landing on heads, divided by 2, the possible outcomes, heads or tails. So 1 divided by 2 equals 0.5. So there's a 0.5 probability of obtaining heads when flipping a coin. That could also be expressed as a 50% chance. Now, the probability of rolling a 2 or less on a 6-sided die would be expressed as 2, the number of ways to get a 2 or less, right? Because I could roll a 1 or I could roll a 2 and satisfy this criterion, divided by 6, the number of possible outcomes for rolling a 6-sided die. And that would yield a probability of 0.33, or 1/3. And that could also be expressed as 33% chance of rolling a 2 or less on a 6-sided die. Now, the probability of me picking a senior at random from a class, let's say there are 6 seniors in a class, would be equal to 6, the number of seniors in a class, divided by 33, the total number of students, or 0.18. This could be expressed as an 18% chance. Now, recall that the normal distribution is just one example of a probability distribution. There are distributions for which the probabilities of scoring in various regions are known, and other ones at that. Now, we initially learned these as percentages of people scoring in various ranges, but dividing these numbers by 100 gets us to the probability of scoring in various ranges. And that would be expressed on a 0 to 1 continuum versus a 0 through 100 continuum. Now, these are both communicating the same information. If a random score were selected from this distribution, how likely would it be for that score to fall within the specified range? Now, most of the time, the number we'll be interested in is the probability of finding a statistic whose value is as or more extreme than one that we found. In other words, information similar to that provided in the percent in tail column in the standard normal table, and the same column, the probability in tail, displayed on the Shiny app for the standard normal distribution. Now, the reason that we will primarily care about the tail probability will become clearer as we proceed through week 4. Now, for Monday, which is September 14th, I want you to study for the quiz. That's quiz 1. It will be posted online on the course page. It will cover material through weeks 1 through 3. It will go live on Monday, September 14th, and will be due Friday, September 18th at 11:59 p.m. Study the Kahoot question sets in order to do well on the quiz. Kahoot question sets will closely but not perfectly match what you see on the quiz. And once you start the quiz, there will be no time limit for how long you have to complete it, as long as it is submitted before the due date. And while taking the quiz, make sure you have the Shiny app for the standard normal distribution open on your computer in a separate window. And feel free to use notes and resources available to you, all of them, while you're taking the quiz. So that means you could have up your formulas for, let's say, the mean, standard deviation, variance, sum of squares, z-scores. And the final thing is just begin prepping for week 4 by reading the specified reading in the course calendar. Good luck on the quiz, and have a great weekend.